So here I'm going to show you how to write the thermochemical equation based on the definition of each enthalpy. So first let's have a look at the enthalpy of formation. Okay, so we have the definition here, the heat change. So the heat here is going to tell us the enthalpy of the reaction, the change in enthalpy of reaction, which is the delta H value. So if we have heat change here, the delta H it can be either positive or negative value. Alright, and then we have when 1 moles of compound is formed. Okay, 1 moles of compound form. So the 1 mole here, the compound form here, we talk about the product. So for example, if you want to form CH4, all right, the CH4 here is it must be in 1 mole. So it is our product. Okay, so 1 moles of compound form from its element. Okay, so how many elements that we have in CH4? So we have carbon and also hydrogen. So carbon, the most stable state of carbon at standard condition is solid. So carbon, solid. Alright, and for hydrogen, the most stable state at standard condition, it cannot stand alone. It is not H atom. It must be the H2 gas molecule. Okay, so since we have 1 carbon here, so here is also 1 mole. Okay, but then we have 4 hydrogen. Alright, so here we need to times it with 2. 2 times 2 is equals to 4. You cannot change the stoichiometric coefficient for this compound because in definition, okay, the compound form must be in 1 mole. So for the thermochemical equation, okay, this is a balanced chemical equation for the formation of CH4. So the thermochemical equation, you just need to add the information about the enthalpy. Alright, so the enthalpy change for enthalpy of formation. Alright, delta H formation for the formation of CH4 is equals to, okay, since it is a heat change, it can be positive or negative kilojoule per mole. That is for enthalpy of formation. Another example, if you want to write down the thermochemical equation for the formation of HNO3. Alright, so let's say you want to have enthalpy of formation for the formation of HNO3. So here we have 3 elements. We have hydrogen, nitrogen, and also oxygen. So the HNO3 must come from its element at their most stable state. So again, hydrogen, the most stable state in their most stable state, it is in gas form, H2 gas. And for nitrogen, it is N2 gas, and for oxygen it is O2 gas. Okay, and then balance the equation. Okay, so since we only need 1 moles of HNO3, here we only need 1 hydrogen, but here we have 2, so times it with 1/2. Nitrogen here is also 1, but here we have 2, so times with 1/2. And for oxygen we need 3 here, but we only have 2 here, so times it with 3/2. So this is the a balanced chemical equation for the formation of HNO3. And to write down the thermochemical equation, just add the delta HF. Okay, so it can be positive or negative kilojoule per mole. Next, we have the enthalpy of combustion. Alright, so the definition is heat released when 1 mole of substance is completely combusted in oxygen gas. So the 1 mole of substance that is combusted, it must be the reactants. Okay, the reactants, you are going to combust it in oxygen gas. So how many moles of the substance that we are going to combust? It must be in 1 mole. So let's say if you have 1 moles of carbon, okay, and then you burn it into oxygen gas, okay, completely, all right. So the carbon dioxide will be formed, all right. So here, balance it. So it's already balanced, okay. The 1 moles of substance that we talk about is here, okay. It must be in 1 mole, all right. And then the thermochemical equation for this reaction is delta H combustion, okay. Since heat release, okay, the delta H value must be in negative, so negative kilojoule per mole, okay. Another example, if you have aluminum, okay, combusted in oxygen completely, okay, it should form Al2O3. Alright, so here the 1 moles of aluminum is completely combusted in oxygen gas. So this one is must be in 1 mole. So you cannot touch this. Okay, but here you have 2 moles of aluminum. So to get 1 aluminum, you have to times it with 1 over 2. Alright, but here the oxygen here you have 3 over 2. Okay, but here you have 2 oxygen gas. So how many moles of oxygen it's gonna be here? Okay, you can solve it like a mathematics. Okay, 1 times 3 over 2. So here we have 3 over 2. But here we have 2 oxygen. So we need the unknown here. Okay, so 2 times it with x. So x is 3 over 4. So we have 3 over 4 of oxygen gas here. Okay, if you times with 3 with 2, we have 6 over 4. Okay, so 6 over 4 is equals to 3 over 2. So yes. And then put the delta H value. Okay, it must be in negative value because heat release. Okay, so this is our thermochemical equation for the combustion of aluminium. For standard enthalpy combustion, right, the definition is still the same, but you need to add at standard condition, which is 180 m and 298 Kelvin. So the combustion will be at standard condition. Okay, so we put the knot here, the delta H naught C. Okay, so to indicate that this is the standard enthalpy of combustion. Next, let's have a look at the enthalpy of atomization. Alright, so heat absorbed. So the delta H should be in positive value when 1 moles of gaseous atom is formed. So here we talk about the gaseous atom form, which is the product. Okay, the gaseous atom form must come from its element. Alright, so let's say if you have sodium, okay, sodium, you want to form 1 moles of sodium gas. Okay, this one, the sodium gas form must be in 1 mole. So the sodium must come from its element. Okay, so the element for sodium, since it is in group 1, okay, it is sodium solid. Okay, so sodium solid forms sodium gas. Okay, the enthalpy here, alright, the value should be in positive kilojoule per mole. Alright, so let's say if you have a chlorine gas atom, you want to form 1 moles of chlorine gas atom. So chlorine from its element, okay, the elements of chlorine is Cl2 gas. Okay, so here it must be in 1 mole. So you need to times this with 1 over 2 so that you have 1 moles of chlorine gas atom. Alright, so write down the enthalpy of atomization value, okay, in positive kilojoule per mole. And for the standard enthalpy of atomization, we just put the knot here. Okay, the definition is still the same, and then you are going to write the way we write down the thermochemical equation is also the same. Just we need to add the standard condition 180 m 298 Kelvin. Okay, so the reaction will occurs at standard condition. And for the enthalpy of neutralization, we have heat release, so delta here should be in negative value. Okay, when 1 moles of water, okay, water formed from the reaction of acid and base, okay, the water form should be in 1 mole. So let's, if you have 1 moles of HCl reacted with 1 mole of sodium hydroxide, okay, we produce 1 moles of NaCl and 1 moles of water. So the definition here is focused on the 1 moles of water form. Okay, and then for the thermochemical equation, just add the enthalpy of neutralization, okay, which is in negative kilojoule per mole because heat is being released. If you have 1 moles of H2SO4 reacts with 1 moles of sodium hydroxide, okay, so now let's focus on the moles of water formed here. Alright, so balance the equation. Alright, so we have 2 moles of Na here, so we need to times it with 2. Alright, and then here if you have 2 OH, alright, so here you have to times it with 2. So this is not a balance, this is not enthalpy of neutralization, the thermochemical equation for the enthalpy of neutralization. So you need to divide all this equation by 2. Alright, so you should half moles of H2SO4 reacted with 1 moles of sodium hydroxide produce half moles of sodium sulfate, alright, and Na2SO4, okay, so that we have 1 moles of water here. So this is a correct thermochemical equation based on the enthalpy of neutralization, okay, because we need the 1 moles of water is formed. Okay, it cannot be 2, it cannot be half, okay, or it cannot be any stoichiometry here. So it must be in 1 mole. So again, if you want the standard enthalpy of neutralization, just add at standard condition 180 m and 298 Kelvin. Okay, and then the delta H here, we are going to put not. For the enthalpy of hydration, okay, so heat release, so again the delta H is in negative value. Okay, when 1 moles of gaseous ion is hydrated in aqueous solution. Okay, so we have 1 moles of gaseous ion hydrated in aqueous solution. Okay, so for example, if you have Na plus gas ion, okay, here it must be 1 mole. In 1 mole, okay, when you hydrated it, it will form Na plus aqueous ion. Okay, so to write down the enthalpy, the thermochemical equation, just add the enthalpy information here, the enthalpy information, okay, the enthalpy of hydration. So since it is energy release or heat release, okay, so it must be in negative kilojoule per mole. And again, to have the standard enthalpy of hydration, okay, we put not here, okay, just at standard condition 180 m and 298 Kelvin. And last but not least, for the enthalpy of solution, okay, so we have the heat change. So the delta H, it can be positive or negative. Okay, so when 1 moles of substance is dissolved in solvent, okay, so we have 1 moles of substance that is dissolved in solvent to form an infinite dilute solution. So right, so let's say the substance that we have is sodium chloride. Okay, so when you dissolve the sodium chloride in solvent, let's say water, okay, you will form an infinite dilute solution, which is Na plus aqueous ion, and also the Cl minus aqueous ion. Okay, so the thermochemical equation, just put the value of delta H solution here. So since heat change, it can be positive or negative kilojoule per mole. Right, so remember the substance that it must be in 1 mole is the sodium chloride. Alright, the substance that we are going to dissolve in solvent. So let's say if you have the magnesium chloride, MgCl2, dissolved in solvent, okay, it will form Mg2 plus ion, aqueous, plus 2 moles of Cl minus ion. Okay, so because we have 2 here, okay, so remember the substance that is dissolved here must be in 1 mole. Alright, and then the delta H solution, again it can be positive or negative kilojoule per mole. So that's it. Thank you for watching.